Transformers dominate sequence modeling, but their core mechanism, attention, is O of n squared. At long context lengths, that quadratic scaling becomes computationally prohibitive. So, what if we could get transformer-level quality at linear time? Mamba, introduced by Albert Gu and Tri Dao in December 2023, does exactly this. It uses selective state-space models with a hardware-aware kernel fusion to achieve state-of-the-art performance. In this video, we will cover state-space model foundations, their predecessor S4, the selective mechanism that defines Mamba, the parallel scan with kernel fusion, the full architecture, and finally, some impressive benchmarks. This session assumes you're comfortable with transformers, attention, RNNs, and basic linear algebra. To understand Mamba, we first need to understand its foundation, the state-space model, or SSM. At its core, an SSM is a system of linear ordinary differential equations. It describes how a hidden state, x of t, evolves over continuous time. The first equation is x prime of t equals a times x of t plus b times u of t. The second is y of t equals c times x of t. Here, u is our input, like a token embedding. X is the hidden state, a vector of dimension n that acts as the system's memory. And y is the output. The matrices A, B, and C define the system's dynamics. A is the state transition matrix, B maps the input into the state, and C maps the state to the output. Think of it this way, X is the memory, U is new information, A dictates how memory evolves on its own, B controls how new information enters, and C is how we read out a useful result from the state. This formulation is incredibly general, any linear time-invariant system can be written this way. So, why are we interested in this specific formulation? Because SSMs provide a unified view of sequence modeling. An RNN, for instance, is just a discrete time SSM. A 1D convolution can also be perfectly represented as an SSM, just with highly structured A, B, and C matrices. This framework is powerful. Let's build an intuition for the state matrix A. Imagine a simple two-dimensional state space. The vector x of t is a point in this space. As time evolves, this point traces a trajectory. The shape of this trajectory is completely determined by A. Different A matrices can lead to stable systems where the state converges to a point, oscillating systems where it circles an origin, or decaying systems where it spirals inwards. The entire game of training an SSM is to learn the A, B, and C parameters so that the state X carries useful, compressed memory of past inputs to predict future outputs. Our models, however, don't operate in continuous time. They see discrete tokens, one after another. So, we need to convert our continuous system into a discrete one. This process is called discretization. A standard method is the zero-order hold, or ZO. It assumes the input U is held constant over a small time step, which we'll call delta. This turns our differential equation into a recurrence relation. The new discrete transition matrix, a bar, is the exponential of delta times A. The new input matrix, B bar, has a more complex form, but it's a well-defined transformation of the original A and B, also dependent on delta. The step size delta is a critical hyperparameter. It represents the sampling rate. A larger delta means we're taking bigger steps in time, capturing longer-range dynamics. A smaller delta means finer-grained, more detailed steps. As we'll see, making this delta parameter learnable and, crucially, input-dependent is one of the core innovations of Mamba. After discretization, we get this simple recurrence relation, x sub t equals a bar times x sub t minus 1 plus b bar times u sub t. The output y sub t is just c times x sub t. If you've worked with RNNs, this should look very familiar. It's a linear RNN. Now, this discrete form gives us two powerful, complementary ways to compute the output. First is the recurrent view. Here, we process the sequence one token at a time, updating the state x at each step. This is incredibly efficient for inference, requiring constant time and memory per step. The second is the convolutional view. If we unroll the recurrence, we can see that the output y is actually a discrete convolution between the input u and a structured filter, or kernel. This view is fantastic for training, because convolutions can be computed in parallel very efficiently using FFTS. This ability to switch between a parallelizable training mode and a fast recurrent inference mode is the superpower of classical SSMs. So, how do state space models actually work? The magic lies in their dual representation as both an RNN and a CNN. In the recurrent view, the state at time t is a function of the previous state and the current input. You can see the equation here, x sub t equals a bar times x sub t minus 1 plus b bar times u sub t. This is inherently sequential, making it extremely fast and memory efficient at inference time. It only needs to keep track of a small fixed-size state. But for training, we can unroll this recurrence. If you expand the equation, the output y becomes a massive convolution. The output vector y is the convolution of the input u with a specific kernel k. This convolutional view is highly parallelizable, perfect for modern GPUs using FFTs. It's the best of both worlds, a fast recurrent mode for inference and a parallel convolutional mode for training. This duality is elegant, but there's a huge problem with this vanilla formulation. It all comes down to the state matrix, A. In theory, A is an n by n matrix, where n is the state size. To compute the convolution kernel, we need to calculate powers of a squared, a cubed, and so on, up to the sequence length. This is computationally expensive. More importantly, it's numerically unstable. If the eigenvalues of a are greater than 1, its powers will explode. If they're less than 1, they will vanish to 0. This is the exact same vanishing and exploding gradient problem that plagues simple RNNs. Without a clever parameterization fora, the model can't maintain long-range dependencies. We need a better matrix. The breakthrough came in 2021 with the S4 model from Albert Gu and his collaborators. S4 stands for Structured State Space for Sequences. The core idea is to give the matrix a specific structure. Instead of a dense matrix, A is parameterized as a diagonal plus low-rank matrix. Crucially, this matrix is initialized using a special construction called the high PPO matrix. High PPO stands for high-order polynomial projection operators. The theory is deep, but the intuition is that high PPO provides a way to continuously update the coefficients of a polynomial that best approximates the history of the input signal. It is a provably optimal way to compress an infinite history into a finite state. This structure allows the state to capture long-range information effectively. And because of the structure, the convolutional kernel can be computed very efficiently in O of n log n time. This made S4 the first SSM to convincingly beat transformers on the challenging long-range arena benchmark. But S4, for all its power, has a fundamental limitation. It is a linear time invariant, or LTI, system. The A, B, and C matrices are fixed. They are determined after training and are the same for every single input and at every single position in the sequence. This means the model's behavior is static. It can't change how it combines information based on the content it's seeing. Think about attention. The attention matrix is dynamically computed based on query key similarities for every token. It's inherently content-aware. S4 is content-agnostic. It applies the same filter everywhere, which is suboptimal. For example, in language, you might want to ignore filler words but remember key entities. S4 can't do that selectively. The fix, and the core idea of Mamba, is to make the system time-varying and data-dependent. We need to make the B, C, and delta parameters functions of the input itself. Welcome to Selective State-Space Models. So, how does Mamba achieve both efficiency and performance? The key lies in its selective mechanism. Let's start with a concrete motivation, the selective copying task. Imagine a sequence of random tokens, where some are special, let's say colored. After a delimiter, the model's job is to reproduce only the colored tokens in order, ignoring everything else. A similar idea is selective induction, where a model should copy a specific token pattern whenever it appears. A standard, static SSM fails miserably at these tasks. Why? Because its state matrices A, B, and char are fixed. Every input token is processed and mixed into the hidden state using the exact same dynamics. There is no mechanism to filter or prioritize information. The core insight of Mamba is to make this selectivity the rule, not the exception. What if the SSM could decide, for each token, what to keep and what to ignore? This is achieved by making the B, C, and delta parameters input dependent. Mamba implements this selectivity in a direct and elegant way. The key SSM parameters are no longer static weights, but are instead parameterized as functions of the input. For each input token, x sub t, we compute new values for our gating quantities. Specifically, the step size delta sub t is calculated by passing x sub t through a linear projection, followed by a softplus activation to ensure it's positive. Similarly, the B and C matrices become B sub t and C sub t, each generated by its own linear projection of x sub t. With these input-dependent values, we can then compute the discretized parameters for the current step. A bar sub t equals the exponential of delta sub t times a. And b bar sub t is derived from delta sub t and b sub t. Now here is a crucial detail: the core state matrix A itself remains a learnable parameter of the model, it is not input-dependent. This restriction is the key that unlocks an efficient parallel algorithm later. The result is that we now have time-varying discrete dynamics. A bar sub t and b bar sub t change at every step, driven by the current token. Among these selective parameters, delta is the most important knob. It functions like a soft, data-dependent gate, controlling how much the current input can influence the hidden state. Let's examine the update for a bar sub t, which is the exponential of delta sub t times a. When delta sub t is large for a particular token, it signifies a large step in the underlying continuous system. This pushes a bar far from the identity matrix, effectively resetting the state and allowing the new input to have a major impact. In other words, the model chooses to pay strong attention to this token. In contrast, when delta sub t is small, a bar is very close to the identity matrix. This means the state barely changes. The system carries over its previous memory, effectively ignoring the current input. This mechanism is a powerful analog to the forget gate in an LSTM, but it emerges naturally from the principles of continuous time systems. On screen, you can see how two different delta sequences, applied to the same input, create dramatically different state trajectories. This power of selectivity, however, comes with a significant computational trade-off. Recall that classic SSMs like S4 had a dual formulation, a recurrent view and a highly parallel convolutional view. That convolutional mode was the secret to their training speed, allowing the entire computation to be framed as one large convolution. But this trick depends on a critical property, linear time invariance. The system's dynamics must be fixed across all time steps. Mamba, by making a bar sub t and b bar sub t input dependent, is explicitly time varying. This breaks the time invariance property, and with it, the convolutional equivalence. The kernel cannot be precomputed because it effectively changes at every step based on the input. This forces us back to the recurrent representation. Naively implemented, this is a major problem. Sequential recurrence is notoriously slow on GPUs, as its O of L complexity cannot be parallelized along the sequence length. This was the core technical challenge Mamba had to solve: how to make this selective, recurrent model fast. The solution is a hardware-aware parallel scan algorithm, which we'll dissect next. So, how do we make this selective scan fast? The recurrence x sub t equals a bar sub t times x sub t minus 1 plus b bar sub t times u sub t looks inherently sequential. Each step depends directly on the previous one. But looks can be deceiving. This recurrence is actually parallelizable. The key insight is to define a special binary operator. Instead of thinking about states X, we think about pairs of A, B that transform one state to the next. Our operator, let's call it star, combines two such sequential transformations. The pair A2, B2 star A1, B1 equals the pair A2 times A1, A2 times B1 plus B2. This composition rule might seem a bit arbitrary, but it has a critical mathematical property: it is associative. Just like addition or multiplication, the grouping of operations doesn't change the final result. This associativity is our ticket to parallelism. It allows us to use a classic divide-and-conquer strategy known as the Blalock-Scan algorithm to compute the entire sequence. The total work remains linear, O of n, but the number of parallel steps is only O of log n. The recurrence may look sequential, but it is fundamentally parallelizable. Let's visualize how this parallel scan works on a sequence of 8 elements. Imagine the input pairs A, B for each time step lined up at the bottom as leaves of a binary tree. The algorithm has two phases. First is the upsweep or reduction phase. At each level of the tree, we combine adjacent pairs using our associative operator. We work our way up from the leaves to the root, calculating partial products. The second phase is the downsweep. Starting from the root with an identity element, we propagate these partial products back down the tree. Each node passes a prefix down to its children, allowing us to compute the correct intermediate state at every single position in the original sequence. The entire computation takes a number of steps proportional to the height of the tree, which is log base 2 of n. So even though the recurrence looks sequential, a GPU can execute the entire scan in O of log n parallel steps with O of n total work. This logarithmic time complexity is what makes training these selective state-space models practical at a large scale. The final piece of the puzzle is hardware-aware implementation. A modern GPU has a memory hierarchy. Each streaming multiprocessor has a small, extremely fast on-chip memory called SRAM and access to the large but much slower main HBM. A naive implementation of the scan would be a disaster. For each time step, it would read the previous state from HBM, compute the new state, and write it back. This constant back and forth between slow and fast memory creates a massive bottleneck. Mamba's hardware-aware algorithm is much smarter. It loads the inputs for a sequence chunk from HBM into fast SRAM just once. Then, it performs the entire parallel scan computation using only that SRAM. Only the final outputs are written back to HBM. This also saves memory by never materializing the full convolutional kernel. For the backward pass, it simply recomputes the scan to save activations. This entire process discretization, scan, and the final projection is fused into a single, optimized CUDA kernel. The result is a dramatic 5 to 10x speedup over a naive implementation. This is comparable in spirit to the efficiency gains that flash attention brought to the transformer world. All right, let's break down the Mamba block itself. It's a single, cohesive unit that takes an input sequence, X, and processes it through a series of steps. First is a linear projection up, which expands the embedding dimension, typically by a factor of 2. This gives the model more space to work with. Next, the expanded tensor passes through a 1D convolution with a very small kernel, like size 4. This is a simple but effective way to capture immediate local context, similar to a CNN. After the convolution, we apply a CLU activation. Then we hit the core component, the Selective State-Space Model, which is the heart of Mamba. This is where the long-range dependencies are handled. In a parallel path, the original input also goes through its own linear projection and CLU activation. This serves as a gating signal. The output of the SSM is then element-wise multiplied by this gate. This step is critical. It allows the model to selectively forget or pass through information. Finally, a linear projection back down brings the output to its original dimension. Together, the convolution handles local structure, the SSM mixes long-range information, and the gate provides powerful, input-dependent nonlinearity. So how do you build a complete language model from these blocks? It's actually much simpler than a transformer. A Mamba model is just a stack of n of these Mamba blocks. We use standard residual connections around each block to aid gradient flow, and an RMS norm is applied before each block begins its computation. Now, here's the critical part: there are no attention layers. And, maybe more surprisingly, there are no MLP or feed-forward layers as we know them from transformers. The selective SSM is responsible for all sequence level or token mixing. And the gating mechanism inside the block, which is based on linear projections, handles the channel mixing and nonlinearity that an MLP would normally provide. So the entire model architecture is just an input embedding followed by n Mamba blocks plus an output projection to get your final logits. Standard sizes published in the paper range from Mamba 130 mm up to 2.8b parameters, trained on diverse datasets like the pile for language, as well as audio and DNA sequences. Let's put a Mamba block side by side with a standard transformer block. The architectural elegance becomes really clear here. A standard transformer block has two main sublayers. First, a layer norm, then multi-head attention for token mixing, followed by a residual connection. Then, another layer norm and an MLP for channel mixing with a final residual connection. That's two distinct, heavy operations per block. Now look at Mamba. It's just an RMS norm, then one Mamba block and a residual connection. That's it. A single, unified operation. For token mixing comparison, the transformer uses attention, which is fundamentally O of n squared in complexity. Mamba uses the selective SSM, which is O of n, or linear time. For the channel mixing comparison, the transformer uses a dedicated multi-layer perceptron. Mamba's functionality is fused into its gated linear projections. The bottom line: the Mamba block runs roughly 2 to 3 times faster per token at inference for a model of matched size, and crucially, it scales linearly to long context lengths where transformers would grind to a halt. So how does Mamba perform in practice? The results are compelling. First, on language modeling, the Mamba paper shows a 3 billion parameter model matching the perplexity of a 7 billion parameter transformer on the pile. That's state-of-the-art performance at less than half the size. Critically, it achieves this with an impressive 5 times higher inference throughput than the equivalent transformer. This advantage becomes even clearer when we look at a plot of perplexity versus model size. Mamba consistently outperforms transformer at every scale. On context length, Mamba's linear time and memory complexity is a game changer. It scales gracefully to over 1 million tokens without the quadratic memory blowup of attention. A plot of throughput versus context length visualizes this perfectly: attention's performance craters, while Mamba's remains flat. Beyond text, Mamba achieves state-of-the-art results on long-sequence audio benchmarks and shows strong performance on genomic data, effectively modeling long-range DNA dependencies. This performance profile creates clear trade-offs. So, what are the strengths? Linear time and memory complexity, state-of-the-art performance on long-sequence modalities, and extremely fast inference. This makes it ideal for audio, genomics, and language. However, its primary weakness is a slight gap on tasks requiring precise copying or associative recall. Standard attention is fundamentally a key-value lookup mechanism, so it excels here. Mamba can struggle with in-context retrieval that attention handles naturally. But this isn't a dead end. Solutions are emerging quickly. The Mamba 2 paper from May 2024 closes some of this gap with improved theory. And hybrid models, like Jamba, strategically interleave Mamba and attention blocks, aiming for the best of both worlds. So, when should you use Mamba? It's a strong choice for any long-sequence application, deployments bottlenecked by KV cache, and for efficient on-device inference where speed and memory are paramount. And that's Mamba. We went from continuous SSMs and ZOH discretization through S4's high PPO initialization to the key insight, the selective scan mechanism. We saw how the parallel scan makes it efficient on modern hardware. For a deeper dive, check the original paper, the new Mamba 2 paper, and the official GitHub. Subscribe and comment on what to cover next, Mamba 2, Jamba, RWKV, or Hyena. Coming up, we'll explore Mamba 2 and the structured state-space duality.